All right, so we're going to do central limit theorem some more, but this time talking about looking at proportions. I get right to the correct screen here. So we're going to talk about a sample and a population proportion. So proportions is really kind of like a percentage. So it's how much of the population has X, Y, Z, whatever it is we're looking at. So in a population, the proportion who have a certain characteristic is called the population proportion. The population proportion is going to be denoted with P. So we use P to mean a population proportion. So in a simple random sample of n individuals, let n be the number in the sample who have the characteristic you're looking for. So the sample proportion we would say is going to be P is equal to X over N. And notice we got a little P hat. So usually when we put a little hat on things, that's because we're saying it's an estimate. So this means this is an estimate of my other P. So this is population proportion P. So this one is to be a true value. We're assuming because this is from the population, so this is the true proportion. And then because this one comes from the sample, this would be the estimated proportion. Kind of like when we were dealing with, or we were in chapter 4 and we were dealing with the linear regression equations, we had that Y hat. Like I said, that hat is just an indicator that we're talking about an estimate. For example, a computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot serve everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 of the 100 people in the sample own a laptop. So the proportion of the sample who have laptops is going to be P hat, and it's going to be 35 over 100. So sometimes we leave it like this. We could simplify it. Just make sure I simplify this correctly. 35 over 100 simplifies to 7 over 20. Okay, yes. Simplify that to 7 over 20, or you could just say it's 0.35. Okay, like I said, because this one is talking about a sample proportion, I'm going to use P hat. So my estimated estimate for the population is going to be, well, it's about 35 or 35% own computers. So we can infer, so we're going to guess that P, the population proportion, is also 0.35. It may not be, but we assume it's probably going to be really close. When we do sampling distributions, we can do sampling distributions. I think I'd said this before, of different kinds of statistics. So a mean, remember, is a type of statistic from a sample. A standard deviation is a statistic that we can make, and a proportion is also a statistic. So any kind of statistic or numerical summary that we can make about data, we can turn into a sampling distribution. So if several samples are drawn from the population, they are likely to have different values of P hat. Like when we were talking about our X bars, we will have different X bars, we'll have different sample means. Because of the value of P hat varies, we can say that P hat is also a random variable, like we could say X bar was, and it has a probability distribution. So here's a distribution of a bunch of P hats. The probability distribution of P hat would be called your sampling distribution of P hat. So this is a sampling distribution of proportions, or before we were doing means. Try to spell proportions, they're proportions. I think I'm gonna start writing that word a little too much. So consider tossing a fair coin 5 times. This produces a sample size of 5, where each item in the sample is either a head or a tail. The proportion of times the coin lands on heads is the sample proportion p hat. The probability that it lands heads each time is going to be about 0.5 or 50%. Therefore, the proportion of heads is going to be 0.5. So next, we're going to look at all 32 possible samples that can be constructed. Like I said, this isn't going to happen every single time that you're going to get half are going to be heads and half are going to be tails. You'll get a variety of other things as well. So we're talking about 2 separate things here. Proportion that lands on heads is the sample proportion. So the probability, so we're talking about if I'm looking at the population, trying to find that data in here. The population P is going to be 0.5. If I'm looking at samples, remember we're doing samples of size 5, we're going to get a bunch of different P hats. Meaning that we could have 0 over coins are going to come up heads. So that'd be 0%. 1 out of 5 could be heads, or 2 out of 5, or 3 out of 5, or 4 out of 5, or all of them. So 1 would be the proportion, could be heads. So this is, like I said, a little bit of a difference here. Like we did when we were talking about the sampling distribution of means, we were comparing to the population of all our data. And so we would get a different value there than we would get here. Because here we're doing a bunch of little samples, and those little samples are going to be all over the place. Okay, so the table displays all samples of size 5 and their sample proportion P. The probability of all values, the mean of all values of P hat, once again, should be just like when we were talking about mean. So we said, so this happens, that the mean of all my sample means is going to be mu. Well, now we're going to look at the mean of all my proportions. And what we expect is that this should match P. So it says the mean of all my P hats is going to be 0.5. So if I took all my different proportions here, and I did a mean of those proportions, we should end up getting back 0.5. So this symbol here is just representing, let me fix that. This symbol here, like I said, it's going to be the same as my population proportion. This is the mean of all the sample proportions. So before we were doing, like here, this was a mean of all my sample means. Like I said, we can have a situation where everything is going to be tails. We have no heads. So the proportion of times that we get tails is 0. We could get 1 head, so 1/5 or 0.2, which we see here and here. We could have 2 out of 5, so 0.4 would be my proportion. We could have 3 out of 4, so that would be 0.6 would be my proportion. We could have 4 out of 8 heads, or 4 out of 5 be heads, which will be 0.8 as my proportion. We're going to have here all heads, so we'd have 0.1. So like I said, we're just getting all those different proportions. So if I took all of these and I add them up and I did my mean, what I should be seeing here is that it's going to be 0.5, which we said is exactly the same as the population proportion. Now, standard deviation, once again, is not going to be as obvious of how we're going to find that. So if I did sigma p hat, this is going to be the standard deviation of all my proportions. Remember, these are all different samples of size 5, so all my sample proportions. And here, when we talk about standard deviations, we were always talking about how important it was to mention the sample size, and we're going to see that again as well. The sample size is going to have an impact on that standard deviation. But if I took all my p hats here and I found my standard deviation, that standard deviation would be 0.2236. Basically, I put all these p's and I put them in a list and I do my 1-var stats. I would expect to see this for a mean and this for a standard deviation. Okay. So this part I'd already mentioned, but in the previous table, we saw that the mean of all my sample proportions was 0.5, but we also know that if I flip a coin, the proportion of times that I expect to get ahead should be 1/2. Like I said, that's looking at if I flip that coin infinite amount of times forever and ever and ever, we should get half of my coin flips are going to be heads. So that probability, or sorry, the population proportion would be 0.5. So the mean of the sample distribution of p hat, so my with all my sample proportions, is denoted by my mu subscript p hat and equals the population proportion. So mu sub p hat equals population proportion. Again, so the reminder, this is mean of sample proportions. P is population proportion. And so we can mention these p hats, those are all my sample proportions. Okay, so for the standard deviation, as we said, that one is not immediately obvious to us how we get that sample, how we can, kind of like what we did with the standard deviation of of sample means, is that there was a connection between a standard deviation of a population and a standard deviation of my sample means. Well, here there should be a connection that we're going to see between proportions and the standard deviation of your sample proportions. And though it's not very obvious, usually what it is this. We have P, the proportion of times that I get ahead. And then we have 1 minus their P. So this is the proportion of times I don't get ahead. And we divide that by the sample size. If I did that, that would get back that standard deviation of my sample proportion. Sigma sub P at, remember, is standard deviation of sample proportions, so my p hats. I think the worst part about this is just you got to keep all these symbols in mind and what's really going on here. Once you kind of get that down, it's a little easier to think about it. But it's that symbology, I think, throws us off more than anything. So that's why I keep writing this down. Like I said, if I want the standard deviation of all my sample proportions, then that is just going to be p minus p times p minus 1. Like I said, oops, we want a different color here. P is population proportion, or how many times the event happens. So we need that. We need the one minus P because that's going to be whatever's left over. And then we divide by N, which is N is sample size. So like I said, we're using a combination of information from my population and information from samples. So if we take P times 1 minus P divided by N, and then we take a square root of that, that will give us the standard deviation. The soft cup drinks at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. I'm not even sure if they do this anymore. The proportion of tickets that are winners is 0.25. So 1/4 of the cups should have a winning ticket. A total of 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let P be the proportion that win a prize. We want to find the mean and standard deviation of P of all my P hats. So we're looking for mean and standard deviation of all sample proportions. So I am going to go in, basically what I'm looking at is like, I'm going to go into whatever fast food chain this is. So let's say it's like McDonald's, go into McDonald's, going to collect 70 people, or maybe I just get 70 drinks, one or the other. And then I'm going to go through and I'm going to see how many of my cups are winners. And we will do this over and over and over again. Each time I do that, that's a different sample that I'm looking at. So the proportion of wins is going to keep changing because sometimes all the cups are going to be winners. It's not very likely, but it could happen. Sometimes you might have no cup as a winner. Maybe 30% of the cups are winners. Maybe 50% of the cups are winners. So we're going to get different population proportions. And what I'm doing is just trying to figure out what the average should be. So my mean of all the possible population proportions that exist, everything that possibly could happen there with my 70 cups, that should equal the population proportion P. And we said right here that for the population, we look across every single food restaurant, looked at every restaurant this chain had, every cup that they sold, and we figured out how many wins we had. That population proportion would be 0.25. We have a sample size is 70. Break that down there. So if I just want that mean of all my proportions, what it should average out to is, can we just back that 0.25? All right, if we want that standard deviation, the standard deviation, if you remember, is going to be the square root of P times 1 minus P divided by N. So the proportion of wins I have is 0.5. And then 1 minus P, that is the proportion of cups that lose, is what that is. We do this kind of like a binomial probability. So we're going to have 1 minus 0.25, so we know it's going to be 0.75. And then we divide by the sample size, and we said here that we're collecting group 70. So if I did this indefinitely, collected every possible group of 70 that I could, what I would find is that among all of those samples, I expect the mean sample proportion to be 0.25 and the mean standard deviation to be 0.5 times 0.75 divided by 70. I forgot what my number is. That is going to be 0.073 approximately. Okay. One more time. So without any more information, we just want to find a mu sub p hat and a sigma sub p hat, so a mean and a standard deviation. A mean of my p hats and a standard dev of my p hats. Okay, so about mu sub p hat, we said that should be equal to the population proportion. So what we got here is that mu p hat is going to be 0.82. The standard deviation, sigma sub p hat, is supposed to be equal to p times 1 minus p over n. So my standard deviation of my p hat of my population proportions will be 0.82 times 1 minus 0.82. And we're told to n, so we're taking samples of size 20. 0.82, 1 minus 0.82 is going to leave me with 0.18. We'll do a big times like that in between so we can know it's multiplication divided by 20. I wrote a number down there wrong. So that is going to be 0.82 times 0.18 divided by 20. So we're looking at doing the square root of 0.00738. Sorry, my calculator did something weird there, which is something in my way there. 0.08. So if I had a distribution of all my of all my samples of size 20, the mean should be 0.82, and the standard deviation should be 0.086. Right. So part of the reason we're talking about doing these proportions here is because later when we talk about hypothesis testing is largely done using either a mean of means or a mean of proportions.